So just a really quick outline. We'll define what this problem is, so what exactly is spatial adjacency, talk about some motivations applications, talk about a couple different algorithms, spatial binning, so classic spatial decomposition algorithm, use of an archery, kind of building off what we were just talking about, and then the use of Python's collections module, so some of those high performance containers and what those can gain us. So what's the question of adjacency? Here's a really simple 1D example. And so all that we're trying to answer is who is next to me. So in a spatial analysis context, this is a really important pre-processing step. We need to know what the spatial structure looks like. Obviously, as this starts to scale, the computation begins to get really expensive. So here's a good 2D example where we're also having to do a high number of computations. So even though this is a pre-processing step, we need to make sure that we're considering this as we're trying to scale our algorithms because we need to be doing this. And so we have this concept of binary spatial adjacency, and we define it primarily in two different ways in the binary case. So either yes, you are my neighbor, or no, you're not my neighbor. In the rook case, we're interested in shared edges. And so it's not enough to answer the question, do I share 2 points with one of my neighbors? Because potentially those 2 points are not a full shared edge. And so we need to go ahead and check, do I have a shared edge with another one of the units? In the queen case, this is probably the case that's of most interest or is most oftenly utilized. And so here, as long as I have one shared vertex, I'm considered a neighbor. Again, this is in the binary case, so we're not using any kind of distance banding or distance thresholds. And so we represent these in the Python spatial analysis library as a spatial weights object. So a list of lists or list of sets, sparse matrices or dense matrices, if you want that representation packed full of zeros. And so the idea behind this data structure is to capture what is the spatial interaction between all the observations in our study area. And so again, I guess continually want to make this point, this is the binary case, so probably one of the easier cases to go ahead and compute. So what's the motivation behind this work that we've been doing? It's an essential pre-processing step, as I said, for a bunch of different algorithms. We'll talk about those at the bottom of the slide. And then computationally expensive once we get to a large enough study area. And so it can become prohibitive to generate these. We use these in spatial regionalization algorithms, measures of spatial autocorrelation, spatial regression, are probably three really common ones, and there are some others. So I just want to talk briefly about what those are. Spatial regionalization, the idea is I have n units or n polygons and I want to aggregate those into k regions. These are known NP hard problems, and so we solve them with heuristic solution methods where there is some, sorry about the wiggle, where there's some constraint, for example, minimization of variance within the region, maximization between the regions, or maximization of compactness, so how circular is my area. Spatial regionalization is quite challenging because we add this contiguity constraint, which is expensive to check, and so obviously then if we have a contiguity constraint, we need to know who is adjacent to who. Within spatial regression models, we're leveraging Tobler's first law, basically suggesting that everything's related to everything else, but near things are more related than more distant things. And so here's a classic spatial lag model where rho is our spatial coefficient or some measure of spatial autocorrelation. We have a spatially lagged dependent variable, and so this W here is what we are trying to compute or what is necessary if we're going to spatially lag these in an epsilon, our error term. So again, I guess in this previous example, once again, we need to know what is the underlying spatial structure. And then measures of spatial autocorrelation. This is global Moran's I. And so here the goal is basically to say what kind of clustering do we have in our data set. In order to do that, I need to know what the spatial adjacency structure is. So binary spatial adjacency is one method to go ahead and compute that. So all three of these require this W object or some representation of the spatial adjacency. Binary adjacency is one option to do this among many others. And again, the cost of generation is non-trivial. My research area focuses on scaling these algorithms to really large data sets. And so that's why this is of interest. If you're working on a small data set, if you're looking at a shapefile with 40 or 50 observations, then just use a really naive algorithm and get it done. But otherwise, they don't scale. Really quick plug that I feel like I need to make. This is all within PySal. And so I think we're going to do a sprint towards the end of the week. This is Python Spatial Analysis Library. If you're going to be doing spatial statistics, definitely check us out and PR back to us. So we're working out of a shapefile format. So how many people are familiar with the shapefile format? All right, cool. So really brief then for everybody else. It's binary, variable, record length. When you get a shapefile, if someone zips it to you, it unzips into a ton of different files. So SHPs are just storing geometries. SHXs are essentially like a fancy offset index that shows you where to look in the SHP. And then the DBF is the old, I believe it's a Microsoft format, the old DBF format. Oh, DBase, sorry, pardon me. So an important thing to note is topology is not stored in these shapefiles. So you can't just look at the shapefile and know what the topological structure is. So you have to derive the topological structure out of the shapefile, unfortunately. So I'm going to talk about a couple different algorithms for doing that. The naive one that you don't want to do, archery, and then binning algorithm. So since we're using shapefiles, we are not going to be leveraging existing spatial indices. So in other words, there is not an archery living in memory on your Postgres that you can just query on, because obviously that's going to be smoking fast and you want to do that. But that data representation doesn't exist. We're looking into a binary shapefile. So in the naive approach, basically the red guy is asking a question, hey, are you my neighbor? Are you my neighbor? Are you my neighbor? This is a hard way to do this. You absolutely do not want to. But in the most naive sense, this is how the algorithm potentially could function. So I'm talking about our archery implementation within PySal here. So that's what we used for some of this testing. So for us, we have to read the geometries out of the shapefile, compute the minimum bounding rectangles. And so this is a pretty efficient representation for then starting to build an archery, but you have to build the minimum bounding rectangle first. So there's an inherent cost in doing that. So then we go ahead and use a really efficient tree representation where we're using a k-means algorithm to go ahead and create this representation. And so this is a really great and it's efficient way to do that, but once again, we have to create it. And we have to create it on the fly as a pre-processing step, because remember that there is no database sitting here. It's efficient to query. And so what I'm going to suggest is if this data is already in a database, just use an archery. We all know that it works and it's fast, but this is for use cases where that data does not exist yet in a spatial database. Binning options, so you can statically bin where I just take a regular grid and lay it over, or you can use something like a quad tree to adaptively bin, but immediately then there is a cost in the creation of this decomposition method, and so you have to take that into consideration when you are selecting a method. The efficiency is a function of the distribution of the spatial density. And so if you have one grid that is exceptionally dense and one grid cell that is very sparse, then we're going to see some interesting computation issues. Let's see. We tried to do this using a parallel implementation as well. Part of the issue there is it's a reading bottleneck, and so we have trouble getting the data out of the shapefile in parallel just because it's variable length binary, and so it is definitely an issue. So why did we go to this high performance container approach? This is in the collections module. So the idea was basically, let's try to remove one of these pre-processing steps where we're computing minimum bounding rectangles. Let's try to use some low asymptotic cost stuff like set intersections, because we know that they're going to be cheaper than a bunch of vertex or edge comparisons. We want to make sure that we're scaling within the limitations of memory, and so obviously as soon as we start paging, forget about it. It's going to take forever to finish. And the primary goal really was, can we beat binning? Is there a better way to do it? And so here's a code example. This is a two-step approach. We're basically setting up a stepper to say, I do want to make sure that I fit into memory, so I don't want to be growing these dicts of sets really, really large. We're going to be representing our adjacency using a polygon ID, and then a set of all those polygons which are going to be considered neighbors. We go ahead and use a vertex counter, again, so that we can make sure that we fit within memory. we create a default dict that is basically a vertex in the queen case. In the rook case, obviously, it's going to be 2 vertices because we need to represent a full edge. And we go ahead and pack that as we're reading the data out of the shapefile. So the idea is just kind of on the fly to read it out. This is all up in a PPy style repo on GitHub too, if you want to look at it. And then finally, once we've packed this kind of intermediary data structure, which is keyed by the vertex or the edge, we go ahead and step over that and say, here's my polygon ID and here are all of my neighbors. And then we can feed this off into PyCell and generate a W object, and we're good to go. So like I said, rook case has to have shared edges, and then here's our keying structure. So essentially identical to the queen case, except we're interested in full edges. So some results, we tested this both on real world data because that's what's of interest and this artificial data. So triangle squares tessellate really nicely. So we figure let's go ahead and use them because we can control for vertex and edge count, average neighbor cardinality, and spatial distribution. And so we go ahead and scale over all these data sizes at the bottom. So rook is in black, queen is in red. We can see that with these artificial data sets, we're significantly outperforming the binning approach. So we're scaling what looks like to be linear at this point, and obviously the binning is not. This is queen case. It gets even more significant in the rook case. Completely with the caveat that we need to make sure we're fitting into memory. And so that's why we're using this stepping issue, or using steppers in our implementation. So that flat linear line at the bottom here, it is again just plotted all by itself so that we can see kind of what's going on. And so we're able to scale up pretty large and still have relatively good run times on the order of just above 30 seconds. We can see that runtime definitely is a function of vertex count, edge count, and potentially neighbor cardinality. So then one of the questions is unfortunately, census tracts, for example, don't just tessellate nicely. You don't just have a whole bunch of triangles. It'd be really nice if you did. And so if we go ahead and we start adding vertices to these geometries, so in other words, we want to control for cardinality, so we want to control for the average number of neighbors, but what happens if I just start chucking tons and tons of vertices in so that my data structures then are going to be getting significantly larger without an impact on how many neighbors I actually have. And so here we can see that the list-based method is outperforming until you hit a vertex threshold. So once these geometries get really, really complex, we start to see that, presumably my working hypothesis is that we're having to allocate huge blocks of contiguous memory, and so that has taken a significant amount of time, and so we see this crossover threshold. So then, for better or worse, we threw it at US census tracts because obviously social scientists are going to be working with real-world data. So I have 2 different results here. So these, I think, are the kind of the most interesting plots. Basically, what we're showing here is geometry count on the lower x-axis, and so we can see that binning is actually more efficient in many of these cases. So there is a crossover point somewhere around 30,000 geometries. So here we're talking about high geometric complexity, higher neighbor cardinality than higher average neighbor cardinality than what we were seeing in the binning approach. We can see too that along the upper x-axis there's a crossover, so there's a quote-unquote sweet spot, if you will, for where our average number of vertices are in the shapefile. And so this is on an Ubuntu machine that had been up for a couple days. So I ran the same exact test on a fresh reboot, asking the question, is this a memory thing that is going on? And which one is more representative for your system? It all depends on how much you're actually going to reboot your computer. I know for me it's the former. For some people it could be the latter. And so here we see that lists are absolutely outperforming in every one of these use cases. And the issue is that we have lots of, I'm assuming, unfragmented RAM that we can just get access to. So we can pack these data structures really well. Python's not trying to find a spot to put a list that we keep growing and growing. So these are all queen case, because queen case is where this is much closer. As soon as you go to rook case, if you're interested in working with edges, this quote-unquote list base or using default dicts significantly outperforms any kind of binning approach. So then where are we going from here? Want to look at profiling and optimizing the R tree. It is such a good data representation that if we could just build it faster, we know that we can query it really fast. So potentially there are some gains to be had on the R tree side. Look at parallel I/O. So this list-based or this default dict-based decomposition method is really amenable to parallelization, and so we could deploy it into a cluster environment without a problem. The issue is you can't read in parallel off of a shapefile, so we're kind of constrained there. So if we can get it into HDFS or HDF5 or into a traditional database, we gain parallel reads, and then suddenly we're off to the races with this algorithm, and we'll be removing the majority of our bottleneck, which is reading. Continuing to try to quantify the impact of memory usage, and so potentially to be able to say, hey, I've set a step size of reading 4 million vertices. Maybe this is too large or too small. Let me go ahead and alter that. So potentially there is a range of good vertex counts. And then since issues of spatial accuracy and spatial error are kind of on the front of our minds frequently, look at fuzzy comparisons to be able to say somebody poorly digitize this data set, but we know that there should be adjacency represented here. So can I go ahead and throw a threshold into this algorithm or into this method and have it be successful? Thanks.